Yeah, it is. Well, you just have to get them out of your system, right? Just like cross the border, they're gone. Okay, so let's talk about expansion. All right, so here we have linear thermal expansion. So here's our thermometer. Here's a little bar of length L naught, and we raise the temperature, and the bar gets longer. Okay, and it gets longer with this equation. So here's the change in length. Here's your original length. All right. Here's your change in temperature, and this thing is called the coefficient of linear expansion. All right, and guess what that depends on?
On
the material, right? Yeah, the material. Because if this is like metal, it expands differently than if it's concrete, which expands differently than if it's plastic, and so on and so forth. So alpha depends on the material, all right? And so just microscopically speaking, right, all particles in a solid vibrate even when it's cold, unless you've gone down to absolute zero. The hotter you make them, the more vibration they do. And since they're bonded together by molecular bonds, you can think of those as little springs. Okay, if they start moving faster, they can stretch the spring a little bit farther, and if that's a whole lattice structure, the whole thing gets bigger. And so it actually doesn't just get bigger in length, it gets bigger in all directions, but this just takes care of length. We also have an equation for like a bulk expansion, like a volume expansion. But depending on the application you're doing, if you're building like a bridge or something, you might need the linear expansion, you might need the bulk expansion. Okay? And here's some so for different materials, right? Aluminum has an alpha of 2.4 times 10 to the negative fifth. These are in Kelvin inverse because you have to cancel Kelvin to get meters again. You see what I mean? An invar? Yeah, sure. Okay. Steel, quartz, glass, all those things. All right. You heat them up, they get bigger. They get bigger by this coefficient. Yeah. What? Yeah, if you make it colder, they get shorter. So, yeah, this can change sign depending on the sign of this. All right. Anybody ever seen one of those?
Yep. Yeah.
Why?
What do you mean why?
Why is this here?
Sorry, to account for expansion.
Yeah, to account for expansion, right? As the bridge gets colder and hotter, maybe not so much in Southern California where our temperature range is a balmy 20 degrees, right? Like, oh, it's freezing, it's 52. Some places have a much bigger temperature range, and so your bridges and things will expand and contract depending on the temperature. You don't want things that expand and smash into other things, because what happens then? Your bridge falls down, and then everybody dies, which is bad. So, yeah. Anyway, this is... we don't need to know this, but I'm showing you this in case you like engineering stuff. So this is force over area. Anyone know what force over area usually gives you?
Yeah.
Kind of. It's pressure, but it also is sometimes called stress. This is something called Young's modulus, which also depends on the material. This is your coefficient of linear expansion. So these are both material-based constants, okay? This has to do with the elasticity, this has to do with the thermal expansion, and this is the change in temperature.
So what's that?
This is the force,
Force over.
cross-sectional area. Yeah. So like if you cut the bridge like this and you looked at the cross-sectional area of the bridge, you'd have the force over that area. That would be the pressure the bridge would feel, and you can measure it with a pressure sensor. Okay. All right. You can also have volume thermal expansion. It looks pretty similar. Your change in volume is now this coefficient times V, your original volume, times change in temperature. And this is your volume expansion coefficient, okay, which is also dependent on material. Yeah. So, what? Glycerin, yes. 49 times 10 to the negative fifth.
Sounds good.
Oh, yeah, there's a demo here that you can do, right, if something expands. So you can get, there's like a ring and a ball. We could do this. I think we have some back there. But you can stick the ball through the ring, and then once you heat the ball up, guess what?
Can't.
Doesn't fit. Yeah, that's what she said. Okay. So, here's a fun question. What happens if ice sinks? Like, specifically to this fish.
These fucks.
That's correct.
Smash.
So, fish smash. I actually made an animation for this. Oh, wait, wait.
no, he's belly up.
So, most things, when they turn into a solid, become denser. Fortunately for us, water does not do that, okay? In a temperature between 0 and 4 degrees Celsius, it decreases in volume with temperature. Sorry, increases in volume with temperature. Water does. Sorry, water expands, and then the ice floats. That's the main point. Ice floats, okay? Yeah. So above 4 degrees Celsius, water expands when heated. So anyway, water has its greatest density at about 4 degrees Celsius. Just throwing that out there. But this is the key to life on Earth, because if you subscribe to this theory of evolution thing, where did everybody start out? Yeah, swimming around in the sea like a fishy. Okay, so microorganisms in water. If everything freezes and the ice falls on it, then not a lot of life survives. Okay. Fun fact. Guess which part of the electromagnetic spectrum you can see underwater? Like if the sun shines on water, which part gets through? Not much. Yellow? It's actually
Gamma.
gamma. No, gamma. It actually
talking about
filters
colors?
gamma.
No, it's
Yeah, the colors get through.
Oh.
So if you look at the if you look at water, it absorbs infrared. It absorbs UV. You know what it doesn't absorb? Light, like the visible spectrum, which is sort of the idea, like that's probably why we see in the visible spectrum, because if you develop the ability to see things while you're underwater, it's not very useful to be able to see infrared or gamma or UV because you're not going to get any. Okay? So out of the things that from the sun that make it underwater, pretty much just the visible spectrum. Yes?
About surface tension. You're talking about things that float.
Uh-huh.
You know, like a leaf floats on the surface.
Um,
Why is that not why ice floats, or
No, ice doesn't float because of surface tension. Ice floats because of density. We'll talk about buoyant force when we talk about fluids, but that has to do with the relative densities of two things. So, for instance, that's why oil floats on top of water. It's not surface tension, it's a density issue. Well,
all the molecules think better?
those are two separate issues. So it's less dense and hydrophobic. So it doesn't mix well, but it also floats. So for instance, if you shake it up, right, you can see it forms little balls, and all the balls float back to the top. So it's two separate issues.